Welcome back, everybody. We're going to take a look at this thing called the fundamental theorem of calculus. Okay, so the first question I have for you is, what is the opposite of taking a derivative? And some of you may know the answer already, and hopefully you're thinking integration. Okay, integration is the opposite. But if you take a moment to think about that, it may not seem all that intuitive. I mean, what does a derivative represent, right? The slope of the tangent line, whereas the bounded integral represents the area between the function and the x-axis. So it's kind of hard to, I don't think it's all that intuitive that the opposite of the slope of a tangent line represents area, okay? But in a more intuitive sense, think about it like this. What is slope? Slope is the change in y over the change in x. That's what a derivative is, dy over dx. That's our f prime, if you will. That's our first derivative. Well, what is dy over dx? That's a ratio. You're looking at the change in y divided by the change in x. What's the opposite of dividing? Multiplying. So if we all of a sudden look at dx times dy, right, if you think of some function, and we're looking now at, say, some change in x, and compare that with now the change in y here, and we multiply those together, well, sure enough, we're getting ourselves some area. Okay, and so algebraically, the opposite of division is multiplication. This is a rate of change. It gives us the slope of the tangent line. This gives us the area when we multiply. Okay? So in an intuitive sense like that, you can kind of see that the opposite of the derivative is the area. Okay? And what the fundamental theorem of calculus does is it kind of explains formally why this works. Okay? I want to show you a couple things here, though. First, let's suppose we have this function on the interval from a to b, okay? And let's suppose we want to find the area under this graph. So I'm, up to some point. So let's say we start at a, and I'm going to draw a line here, and I'm going to call this some value x, okay? And so I'm going to let a of x represent the area under the graph of f from a to x. So in other words, this would be the bounded integral from a to x of this f function. And instead of calling that the x-axis, I'm just going to call it the t-axis, because I'm using the letter x as a variable here. Okay, so a of x represents the area under the graph of f from a to x. Well, let me come up above x a little bit and call this guy x plus delta x. So this little difference right here is what we're calling delta x. So then the area from a all the way up to x plus delta x would be notated like this, okay? And that represents the area under f from a to x plus delta x under the graph of this f function, okay? Well, what I want to focus on is this little strip in between the two, okay? Let's focus on this right here, okay? And what I'm going to do is draw a rectangle in. And the area of this rectangle can be used to approximate the area of this strip under f from x to x plus delta x, okay? And we can see that that rectangle is going to be a slight under approximation the way I've drawn this here, okay? But let's think about this. If I want to get the exact area of this region right here, I would take all of this area and I would subtract that area, and it would just leave me with the area in between the two. So the actual area can be written as a of x plus delta x minus a of x. And that will be approximated by the area of this rectangle. Well, the area of the rectangle is base times height, right? The height of this thing is going up to the function at x. That's f of x. The base of this thing is that length from x to x plus delta x, or just delta x. That's the width of the rectangle. Okay, so the exact area on the left can be approximated by the area of this rectangle. Well, what I'd like to do algebraically is get f by itself. So to do that, I'm going to divide both sides by delta x. Okay, so here I'm just dividing both sides by delta x. Okay? Well, what can we do to make this approximation really, really good is we can, what do you suppose we're going to do with delta x? We're going to let delta x approach 0. We're going to make this region as small as possible. So I'm going to bring this blue line back back even further. Okay, let's see if I can get the animation here right. So if I bring this blue line back to the left closer and closer and closer to the actual x value, that rectangle that we're using to approximate the area between gets really, really skinny, okay? And we're going to get a very, very good approximation then for the, you know, this left side and right side, if you will, that we're looking at down here, okay, if we let the limit approach 0. And I don't know why my app keeps crashing. This happened again yesterday, so give me just a second. And here we go. Okay, so the idea is if we want these things to be equal, we're going to let the limit as delta x approaches 0 of both sides. So we're going to take the limit as delta x approaches 0 of this, and that's going to equal the limit as delta x approaches 0 of f of x. Well, on the left-hand side, this is precisely the limit that represents the definition of derivative. And in this case, this would be the derivative of that a function. So on the left, I can write that as a prime of x. On the right-hand side, I don't have a delta x in this function. So whatever delta x approaches, f of x is still just going to be f of x. And what we get in this geometric sense is this conclusion, which might not seem like a lot, but it's a big deal. A prime of x equals f of x. Remember, a to begin with was the area. A was the integral. If we take the derivative of the integral, we get the original function back. Okay? So this is saying that there is an inverse relationship between integration and differentiation. Okay? And that's kind of the sense of what the fundamental theorem of calculus is getting at. It's making the point that derivatives and integrals are inverse operations of each other. And again, this might not be the most clear way to see that, but that's indeed what this is saying at the end of the day. If we take the derivative of the integral from a to x of this f function, as I've called it, the derivative of the integral, they more or less cancel back, and we get back this original f of x function, right? When two things cancel out, they're inverses, we get back what we started with. Okay, so the big gist here is that, again, you know, derivatives and integrals are inverse operations of one another, and it's kind of neat to see how they're related. Now, the official fundamental theorem of calculus states the following, and there's two parts to this, and we're going to deal with the part that shows us how to evaluate bounded integrals, okay? And that's what this is getting at right here, the fundamental theorem of calculus. Let f be continuous on a closed interval ab. If capital F is an antiderivative of f, meaning if we integrate little f and we get back this other function we're calling capital F, then the bounded integral from a to b of little f of x dx is given by f of b minus f of a. This is how we deal with bounded integrals. And what this is saying is that you integrate the function first that's in here. See this thing? Integrate it. Then evaluate the antiderivative at the top and bottom bounds and subtract. Okay? And this is now moving forward how we're going to be able to find the exact area under a curve. Okay, we're not going to have to do these crazy limits anymore to do this. Okay, now let me try to walk you through the proof of the theorem to see why this works. Okay, so let's suppose I have some capital function f, I'm calling it, on the interval ab. Here's f of a, the y value at a. Here's f of b, the y value at b. Our job is to show that f of b minus f of a is going to give us the integral of lowercase f, okay? So remember, capital F is implied to be the antiderivative, okay? The trick now to getting to see that this works is finding a convenient way to represent this difference, okay? So it might seem weird, but what I'm going to do is I'm actually going to find, like, tons and tons of points on this capital F function, okay? I'm going to let this be x sub 0, and this is going to be x sub n. This would be x sub n minus 1, x sub n minus 2, x sub n minus 3. This is x0, x1, x2, x3, all these different x values that we're using to partition, okay? Well, look at how I'm going to rewrite f of b minus f of a. Notice that f of a itself is the f value at x sub 0, so I can say that f of a can be written as f of x0. And the y value at b can be written as the y value at our last x value, f of x sub n. Okay, b and x sub n are the same, a and x sub 0 are the same. So look, here's how I'm going to rewrite this difference. I'm going to write it like this. I could think of this as f of x sub n minus f of x sub 0, but I'm going to add a whole bunch of other terms in. So watch this. It's going to be f of x sub n minus f of x sub n minus 1. Plus f of x sub n minus 1 minus f of x sub n minus 2 plus f of x sub n minus 2. And basically what I'm doing is with all these, I'm subtracting and adding the same values over and over again because they would essentially cancel out until we get to say, okay, now we're at minus f of x sub 1 plus f of x sub 1 minus f of x sub 0. All these middle terms are going to end up canceling out, and at the end of the day, we still have f of x sub n, which was f of b, minus f of x sub 0, which was f of a. Okay? So hopefully you see that all these middle terms would end up canceling out, but there's a reason we want to write it this way. What I can now do is I can like group these things together like so, and we can write this as a summation, okay? So what we have now is that f of b minus f of a, which equaled this long, ugly thing I just wrote, can be cleaned up into the summation as I goes from 1 to n of capital F of x sub I minus capital F of x sub I minus 1. All right, that's what all this can be simplified as. And think about it, if I start plugging in the values, if I plug 1 into this thing, I get f of x1 minus f of x0. That took care of that last term. When I plug 2 in, I get f of x2 minus f of x1. That would be the term before it, until I get to n, where I get f of xn minus f of x sub n minus 1, which was the first term. Okay, so kind of the summation ends up rewriting the terms backwards, but that's okay. It's all the same thing. All right, so bear with me on this proof. Again, some technical stuff here. So f of a minus f of b represents this particular summation. Okay, now, since capital F is a continuous function and differentiable, it must be differentiable because it's the antiderivative of the little f function, we can apply the mean value theorem. There must be some x value I'm going to call c sub I on the ith subinterval such that f prime of c sub I equals the average rate of change of f over that interval. Okay, and we get that. Well, the derivative of capital F can simply be written as lowercase f, right? The derivative of big F is what we're saying is little f. So I'm just going to clean that up and write little f of c sub I. So now we're bringing the little f function into the game, okay? And this difference in the denominator, that's just our partition, like x sub I minus 1 and x sub I. We're just finding the length of the partition. And if we assume equal subintervals, we can just call that our delta x. Okay, so the denominators are change in x. All right, and if I want to get this by itself, I can multiply both sides by delta x. Okay, and that would then say f of c sub I times delta x equals this particular difference. Okay, but where do we see this particular difference? That is precisely what's inside of our summation here. So I can replace this with fc sub I delta x. So let's do that. So kind of picking up where I left off, f of b minus f of a equals now the summation as I goes from 1 to n, and again I'm replacing this difference with what it equals, fc sub I delta x. Okay? And moving forward now, what do we want to do to get this approximation to be as good as possible? We want to let the limit, we want to look at the limit as n goes to infinity. So what we can now do is take a look at this. We're going to look at the limit now as n approaches infinity of this. Again, we're making an infinite number of rectangles with infinitesimally small widths. But now look at this particular limit, folks. This is precisely the definition of your bounded integral. And so now if we sub in for that, we get that f of b minus f of a is equal to the integral from a to b of little f of x dx. And that concludes the proof, okay? And again, this isn't something you're ever going to have to show on your own. This is more like if you major in math in college and you go on to take third and fourth year courses, you do a lot more of this kind of stuff. But this is just me trying to show you, yeah, this is legit and this works. Okay, so now let's actually apply the fundamental theorem of calc and see how we evaluate bounded integrals without using limits, okay? So you'll see questions similar in WebAssign, so let's go through a bunch. Evaluate the definite integrals of the algebraic functions. Okay, so first I have the integral from 2 to 5 of 3 with respect to x. So, first, let me show you how this works, okay? So this is like what we're calling our little f function. And it says, okay, find the antiderivative. If I integrate 3 with respect to x, I get back 3x plus our arbitrary constant. Okay? And that's the antiderivative. This is like what we're calling the capital F function above. Now what I need to do is evaluate this from 2 to 5. That's called the evaluation bar. And what the theorem says is find the antiderivative, plug in the upper bound, plug in the lower bound, and subtract. So we always plug in the upper bound first. So I'm going to plug 5 in for x, and then I'm going to plug 2 in for x. And now we get 15 plus c minus 6 plus c in the parentheses, and 15 minus 6 is 9. And what do you notice about the c's? When I distribute, the c's are going to cancel out. And that is always going to happen to the arbitrary constant with a bounded integral. They will always cancel out. You shouldn't have a c left over, and you get back what's the dead-on area, which in this case is 9. Now I start with this example because I can easily verify it geometrically to you. Think about it. The line y equals 3 is just a horizontal line up at 3, and we're on the interval from 2 to 5. So I just have a horizontal line up there on the interval from 2 to 5. Well, we're dealing with a rectangle whose height is 3, whose base is 3, and sure enough, the area is 9 units on the nose. Okay, so the bounded integrals give us that. Okay, part B, let's find the area under the graph of y equals x from 0 to 4. So again, find the antiderivative. If we integrate x to the first, we get x squared over 2. We don't need to worry about the plus c here. So I'm going to evaluate this from 0 to 4. So I'm going to have 4 squared over 2 minus 0 squared over 2. 16 over 2 is 8, minus 0 is 8 units on the nose. Again, something we can verify geometrically. The line y equals x goes through the origin, and I'm on the interval from 0 to 4. It looks like we're really just finding the area of that triangle. 1/2, base is 4. Let's see, if y equals x, then that y value is 4. So we get 1/2, 4 times 4. Sure enough, we get back 8 again. Okay, so again, just kind of the first two examples. You can see the geometry works with the calculus. And for the rest, we'll just do the calculus, okay? So next up, let's find the area under the graph of y equals x squared from 0 to 2. So again, we'll start with the antiderivative. Add 1 and divide by the new power and evaluate from 0 to 2. 2 cubed over 3 minus 0 cubed over 3 leaves us with 8/3 area. And you may remember this because this was in our formal limit definition of area. We got the same exact result. This is a lot easier, though, I think you'll agree, than doing those limits. Okay, let's look at the area under the graph of sine theta from 0 to pi. Now look, notice it's not x's, it's thetas. Theta is the variable here, is given by d theta. Okay, just be on the lookout for that stuff. It can be any letter in the world. All right, if you think about the sine function, looks like this, and we're looking for the area from 0 to pi, so I'm looking for that chunk area there. I would expect this value to come back positive since it lies entirely above the x-axis. Let's see. What's the antiderivative of the sine function? Negative cosine of theta. And we're going to evaluate from 0 to pi. Watch out for the negatives. We're going to have negative cosine of pi minus the negative cosine of 0 when I do top minus bottom. Watch the double negative. Cosine of pi, negative 1. Cosine of 0, positive 1. Turns out there is exactly 2 square units of area under the sine curve from 0 to pi. Okay. Okay, next up, area under secant squared x from 0 to pi over 4. So again, find the antiderivative. What is secant squared the derivative of? The tangent function. So we get tan x from 0 to pi over 4. We're going to get tan pi over 4 minus the tangent of 0. And again, work on your values. Tangent of pi over 4 is a very nice value. That's 1. Tangent of 0 is also nice. That's 0. And so we get exactly 1 square unit of area under the secant squared function from 0 to pi over 4. Okay, in the next couple of examples, we'll deal with having to clean things up a little bit. Okay, again, watch out for products, quotients, chains. We have some rules for dealing with that stuff in integration, but nothing we've learned yet. So if you see something squared, like to take the derivative, that would be a chain rule. Well, we got to clean this up first. So you may remember from the unbounded integral lesson, if something's squared, for now we got to clean it up. So here we're going to rewrite this. If I square that out, we're going to get 4t squared plus 4t plus 1. And again, I just chose t as the variable just to change it up a little bit. So we're integrating with respect to t here. And now in doing so, we're going to get, it looks like 4t to the third over 3 plus 4t to the second over 2 plus 1t evaluated from 0 to 2. Plugging in the 2, we're going to get 4 times 2 cubed over 3. I'm just going to simplify that to 2t squared. Okay, there's the top, and then, you know, here we're going to get 0 when we plug zeros in to all those terms. So cleaning up the first, let's see, we get, looks like 8 times 4 is 32 over 3, plus another 8, plus another 2, so plus 10, which I'll write as 30 over 3, and it looks like we get 62/3 area at the end of the day. Okay, next up in part G, I want the integral from 1 to 4 of 1 over x squared plus 2. Again, when we see x's in the denominator, let's rewrite those with the appropriate power. So this becomes integral 1 to 4 of x to the negative second plus 2. Okay, add 1 and divide by the new power, and the 2 becomes a 2x, and we're evaluating from 1 to 4. Okay, I'm going to rewrite this. X in the denominator, the whole thing's negative, so negative 1 over x plus 2x from 1 to 4. Plugging in the upper bound, negative 1 over 4 plus 2 times 4 is 8, minus plugging in the 1, negative 1 over 1 plus 2 times 1 is 2. So we got negative a quarter plus 8, and then negative 1 plus 2 is a minus 1 at the end, okay? So negative 1 quarter plus 7, negative 1 quarter plus 28 quarters is 27 fourths at the end of the day, okay? And if you feel like I've made a mistake on anything, just reach out to me, okay? And I can try to fix those. But I think these are looking pretty good. Okay, next up, we have the integral from 4 to 9 of u plus 1 over the square root of u du. So here the variable's just u. All right, now we have a quotient, okay? So what we got to do is we got to clean up this quotient, and I'm going to do that by, you know, breaking this up into separate terms and then cleaning it up a little bit, okay? So we have integral 4 to 9, u to the first over the square root of u. That's u to the 1 over u to the 1/2. When we divide, we subtract. We get back u to the 1/2. First term, u to the 1/2. Here we have u to the 1/2 in the denominator. That's u to the negative 1/2. Okay, so we took a moment to clean up the original integrand, the stuff inside the integral, and now we can integrate using power rule. U to the 1/2. If I add 1, I get u to the 3/2 over 3/2. So that, in other words, that's 2/3 out front. U to the negative 1/2. When I add 1, I get positive 1/2 divided by 1/2, which is a positive 2 out front. Okay, and if you need to slow down and write that out, do so. And now we can evaluate. So we're going to have 2/3 of 9 to the 3/2 plus 2 times 9 to the 1/2 minus quantity 2/3 of 4 to the 3/2 plus 2 times 4 to the 1/2. All right. 3/2 power. Take the square root of 9 and cube it. So 3 cubed is 27 times 2 is 54. Divided by the 3 is 18, I want to say. But I'm just going to double check that. 9 to the 3/2 is 27. Divided by 3 times 2 is 18. Okay, so first term is 18. Let's see, plus. Here we have the square root of 9 is 3 times 2 is 6. minus, okay, 4, square root is 2, cubed it is 8, times 2 is 16 over 3. And square root of 4 is 2, times the other 2 is 4. And so it looks like we've got 24 minus 16 thirds minus the 4 is 20 minus 16 thirds is 60 thirds minus 16 thirds is 44 thirds. All right. All right. Now, the next two examples deal with absolute value functions, okay? Now, let me kind of illustrate these geometrically for you, okay? I'm just going to clean some of this up so I have a little more room. If you need to rewind to see that, go for it, okay? Now, typically what we got to do is we got to remember that this is really two lines, okay? If you think about it, you know, absolute value of x minus 3 would be the absolute value of x graph shifted right 3 units. And so we have this v. And in this example, I want to find the area under this graph from 0 to 4, all right? Well, you know, one thing I could do is I could actually write this out as a piecewise function, okay? At x equals 3, this thing splits up. So that's how I set up that. When x is less than 3, the values in here are initially negative, so I have to negate that, giving me negative x plus 3. That's actually the equation of that line. When x is bigger than 3, these values are already positive. I drop the bars and just get back x minus 3. That's the equation of this line. And now what I could do to do this single integral is say, all right, I could do the integral from 0 to 3 of negative x plus 3. That will give me that area. To it, I can add the integral from 3 to 4 of the x minus 3 function. And I could work both these integrals out, and it would take a couple minutes to do so, and I could add those areas together, okay? I'm not actually going to do that because I think there's a much easier way to find these areas. What kind of shapes are we dealing with? Right triangles. So instead of, you know, obfuscating this or making it more complicated than it needs to be, you know, typically with these linear absolute value functions, what I will do is I will sketch it like I did, and then I will just find the areas of the two right triangles that were formed, okay? So I'll highlight the first one in red. That would be this. But again, you don't really need to write that out. Basically what I would be doing is saying, look, this equals, I'm setting up 1/2 base times height for the first triangle plus 1/2 base times height for the second. Base of the first one goes from 0 to 3, so that has a base of 3. Now the height is this y value at 0. So if I do f of 0, absolute value of 0 minus 3 ends up being 3. So the height there is 3. For the second base, I'm going from 3 to 4, so that's a length of 1. The height is going up to the function at 4. Okay, label that one blue. There's that. That's the one we're working on here. There's the first one. Okay, just color code things. But look, the height here, height 2, if you will, I'm going up to the function at 4, so that's going to be f of 4. Absolute value of 4 minus 3 is 1. So plug in 0, plug in 4. You're essentially plugging in the bounds to get the heights. And now we can easily put this together. We got 9/2 for the first one plus 1/2 for the second for a grand total area of 5 units, right? 10/2. All right, so the geometric approach to these I think is much better. Let's do the same thing for the next example here in part J. So I've got absolute value of 2x minus plus 1. So to see where it splits, it always splits when it touches the x-axis, which is to set it equal to 0. So I set what's in the bars equal to 0. Here I'm going to get negative 1/2. That's where this thing is going to split up. So if I go to sketch the graph, I'm integrating from negative 1 up to 3, and at negative 1/2 is where this v splits up. So here's this absolute value function. Okay, looking something like this. All right, and again, I'm going to cut it off at the bounds, negative 1 and positive 3, and I'm going to find the area of the two right triangles. So this is going to equal 1/2 base times height for the first plus 1/2 base times height for the second. Base 1 goes from negative 1/2 to negative 1/2. That's a length of 1/2. Height 1 is going up to the function at x equals negative 1. So I'm going to look at f of negative 1, plug it into the original function. Let's see, I get negative 2 plus 1 is negative 1 in the bars, which is positive 1. Don't forget to take the absolute value. So here the height was 1. Okay, base 2 goes from negative 1/2 to 3. That's a length of 3.5, 3.5 or 7/2, whatever you prefer. The height is going up to the function at 3. So I'm going to look at f of 3. That's the absolute value at 2 times 3 plus 1. That comes back a height of 7 here. Now I've got the dimensions of the triangles. I've got the area. It looks like 1 over 4 plus 49 over 4 for a total of 50/4 or 25/2 area. So that's my recommendation for dealing with integral values of absolute value functions, okay? For the rest, we're finding ways to use our power rule or playing off our trig integration properties, okay? Couple other problems here. Determine the area of the region under the graph of y equals x squared plus cosine of x on the interval from 0 to pi. So I don't even know what the graph looks like, and I don't care at this point because now I have a good understanding of how to find the area. So I'm going to set up the bounded integral from 0 to pi of this particular function. Integrating x squared, we're going to get x cubed over 3, or 1/3 x cubed. Integral of cosine is positive sine. Since it's bounded, we don't need the plus c, and we can evaluate from 0 to pi. Plugging in the upper bound, we're going to get 1/3 of pi cubed plus the sine of pi. There's top minus 1/3 of 0 cubed plus the sine of 0. And what's nice is that 3 out of 4 of these terms equal 0. Sine of 0 is 0, 0 cubed is 0, sine of pi is 0, and it looks like the area ends up being 1/3 of pi cubed. Okay, and then last but not least, find capital F is a function of x and evaluate it at x equals 1, 3, and 4. Capital F is given, capital F of x is the integral from 1 to x of t squared minus 2t dt. So if we're looking at the graph of t squared minus 2t, this capital F function represents the area under that graph from 1 to whatever x value we give it. So we can find the antiderivative, we can find f of 1, f of 3, f of 4. Okay, so one way to find the antiderivative is to just integrate this thing as it is, all right? So we want capital F, it's this integral. Well, let's integrate it. If I integrate this with respect to t, I'm going to get 1/3 t cubed minus 2t squared over 2, or just t squared, okay? And that is evaluated from 1 to x. So let's see what we get. Now, it might look a little weird, but first thing we're going to do is plug x in for t. And so we're going to get 1/3 x cubed minus x squared. There's the top, minus. Now we're going to plug the 1 in. We're going to get 1/3 of 1 cubed, that's just a third, minus 1 squared, which is 1. And so I can write this as 1/3 x cubed minus x squared minus, this is what, negative 2/3, so we get a plus 2/3 with the double negative out of that. And there is the f function. What's f of 1 going to be? Well, now that I have the f function, I could go ahead and plug 1 into that thing. But if you also pay attention to the bounds, think about what f of 1 is going to be. If f is the integral from 1 to x, and I do the integral from 1 to 1, what should the answer be? I think the answer is going to be 0. But if we do it out according to the formula, let's see. We get 1/3 of 1 cubed minus 1 squared plus 2/3. We get 1/3 minus 3/3 plus 2/3, which is indeed 0. Look at that. Okay, so again, the properties of the bounds being equal gave us that. But either way, once you get this f function, you can just plug numbers into it now. And in f of 3 then, if I want f of 3, that's going to be 1/3 of 3 cubed minus 3 squared plus 2/3 is, let's see, 9 minus 9 plus 2/3 is just 2/3. And last but not least, f of 4 is going to be 1/3 of 4 cubed minus 4 squared plus 2/3, 64/3 minus 16 plus 2/3 minus 48/3 plus 2/3. Let's see, 64 minus 48 is 16, plus 2 is 18, and divide by 3, and it looks like the answer there should just be 6. All right, folks, so a little bit different on the last one. They gave you f as a bounded integral. We worked it out in terms of x, and then we're able to evaluate it anywhere we wanted. All right. Let me know if you have any questions, folks. Try the homework problems, and we got plenty more to go.